Thank you and good morning. Do you guys all have a favorite trigonometric function? And it's hard to choose, isn't it? Do you want to guess what mine is? It's the hyperbolic tangent. Yeah, that's the thing. I take them all the time. So I do have a written talk, and I will try to stick to my notes, but as I get more passionate in my speech, I tend to take advantage of the tangent. The truth will set you free. What fields are better suited to delivering on that promise than science, technology, engineering, and mathematics? In fact, I would argue they are the privileged source of truth in the 21st century. We see it in our language when we say things like, studies show, hard facts. Scientists now know, more research is needed. We see it in public policy debates when we employ studies of effectiveness, when we vote on how to allocate funding, and when we argue crisis issues. We rage over climate change, peak oil, fracking, net neutrality, autonomous driving, workforce automation, H-1B visas, access to affordable life-saving medication. I don't know how you feel about the looming literary apocalypse or the puzzling geometry of modern architecture, but they don't get much airtime compared to those other issues. We've extended even the Gothic cautionary tale into its own genre of post-apocalyptic literature. We have movies like Maze Runner and books like Cormac McCarthy's The Road to warn us about the dangers of doing science wrong. Most of us in contemporary society believe that when science is pursued correctly, scientific truth is credible, reliable, and impartial. It's credible because the methodology is transparent and it permits others to reproduce our results. It's reliable because we can apply the results that we've discovered in the laboratory via technology to the world to achieve predictable results. And it's impartial because the results that we obtain do not depend on the desires, beliefs, or superstitions of the researchers. William Thomson, the first Baron Kelvin, whom we know today as Lord Kelvin, was a 19th century Scots-Irish physicist, and he's the engineer after whom the absolute temperature scale is named. This is what he said: when you can measure what you're speaking about and express it in numbers, you know something about it. When you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science. And I believe this is why the number of followers, likes, and retweets is so important. We need that number. This privileged truth extends even into many high school programs that have highly integrated liberal arts. Math and science stand apart. They follow their own internal development. They progress according to one of the generally accepted contemporary grade plans. And they retain the modern categories of the programs that you find all around the country. And by that I mean biology, chemistry, physics. There does not seem to be any broad contemporary approach to try and cross-fertilize what's studied in STEM with the rest of the curriculum. After all, what has cellular respiration got to do with Dickens? The efforts to add in the arts in so-called STEAM programs is still at the service of the original four. As one STEAM website puts it, students in STEM programs may have more experiential learning opportunities, but they're limited to only science, technology, engineering, and math. Our economy requires so much more than an understanding of these areas. It requires application, creation, and ingenuity. STEM alone does not foster these essential nutrients. Apparently, the only reason that we study the arts is so that we can do STEM better. Innovation is the current battle cry of the industrialized nations, meeting the challenges of the 21st century. I live very close to College Park, Maryland, so I see the University of Maryland's current slogan all over the place: Fearless ideas that start with a spark and lead to innovation and an entrepreneurial spirit that few can compete with. If we can achieve science, unalloyed science, purified of the unscientific complications that hold it back, then we believe it could solve all of our problems. In theory, there's no disease medical research could not cure. We could possibly even cheat death indefinitely. In the future, we'll have the possibility of not needing to work. Many of us could potentially live lives of leisure. When everyone is sufficiently educated, there will be an end to intolerance and the baseless constraints imposed by religious and cultural rules that have no basis in fact. But there will be no conflict because we'll eliminate the roots of poverty and inequality. This is the futuristic utopia that I call the Star Trek society. It's post-scarcity, it's moneyless, it's a galaxy-spanning civilization whose flagship technology, the Enterprise, is used to find people and invite them to join the Federation. And we're building our way there already. How many products have you heard about that promise to release you from drudgery? They'll give you your time back so that you can focus on things that are really important, whatever that means to you individually. Our next great horizon is machine learning and artificial intelligence. Cars will drive better than humans in 10 years. Most repetitive, servile tasks will be automated. Machines will learn under complex algorithms and perform tasks that humans find intractable. Even creativity is being reduced to models. As for originality, there's an algorithm for that too. What we really need is an educational system that can take us the last few miles. That means years of the fundamentals, basic math and science building blocks that will help select and focus the student body. In the first world, we've already developed an extremely refined approach. We abstract facts and techniques from all the distracting context and present them in their most essential forms. We then enumerate objectives and grade level and assess a mastery of these building blocks in isolation in this ever-growing series of standardized tests. The top 10% will promote to Tier 1 educational institutions. They'll benefit from top funding, they'll use state-of-the-art equipment, they'll occupy the newest buildings on campus. Those that make it through the weed-out courses their freshman year, and statistics show that's just about half of them, will go on for further selection in projects and advanced studies. Our goal is to educate an elite force of advanced researchers to discover new truths about the universe and a complementary force of technologists to transform those truths into products and pastimes. Facts supported by research and applicable through technology to the manipulation of the natural world is the privileged source of knowledge that will lead us to the freedom of lives unburdened by drudgery and conflict, unimpeded even by our own bodies. The truth will set us free. Permit me to give you another inconvenient truth. Most students, and increasingly most adults, will be left behind. They'll lack sufficient understanding to distinguish between credible science and quackery. They'll have far less intuition about what is actually true than humans have ever had about their world. Witness the explosion of news and internet sources that fact check. How often do these actually change the opinions of the people who read them? And how often are they just accused of being part of the conspiracy? Concerted campaigns of disinformation launched from multiple social media accounts can create entirely fabricated news events about things that never happened. Retractions and corrections go unnoticed, while misinformations and accusations go viral. It's already possible to find consumer products that can electronically duplicate a voice speaking arbitrary text. They record you for about a minute, and then they can have you read back Shakespeare, and it sounds just like you. How much longer before the technology that can bring dead actors into contemporary roles is available for your amusement and extortion? Additionally, there are many, many, many studies that have leaned so far forward in order to get published that their results are irreproducible. They make their rounds quickly nonetheless via the internet. They have their effect on our fears. They impel us to change our diet, boycott companies, and race to buy something before it's too late. most of us will be so far removed from the workings of the technology that we use every day, that we have come to depend upon, that we'll be entirely beholden to the fabricators and vendors that give them to us in an increasing cadence. We'll run our children through stressful college preparatory courses, standardized tests, experiential learning, internships, and extracurriculars. They'll forget more than half of what they studied during late-night cram sessions, where they're struggling to stay awake and adequately nourished. Very few of them will end up at the forefront of a scientific field. Many of them will find it difficult to realize themselves in meaningful work and will live in constant fear that their job will be done more efficiently and cost-effectively by machines. And perhaps most sadly of all, few will have had sufficient liberal education to question that this is the way things ought to be. The truth might make you cry. I've worked in technology for the past 20 years, primarily in software development and cybersecurity, both for the private sector and for higher education. I've worked alongside technologists who were trained in the 70s, as well as students who graduated in May. As you might imagine, many of the people who work in the technology field are extremely optimistic about technology. For the most part, they also fancy themselves data-driven decision makers. When technology cannot solve a problem, they'll typically point to ineffective implementation, insufficient funding, obstinate users, in short, anything but the inadequacy of the technology itself to solve the problem. If you point out that technology created most of the crises they think science can solve, they'll reply it's human greed or hunger for power that creates the problem. And of course, they're right. But somehow it never occurs to them that the way we teach and promote STEM education could be part of the problem. I've never worked for a premier tech company like Amazon or Apple or Netflix or Tesla. The organizations, private and academic, that I've worked for have a far more representative sample of applicants and employees. These are the students that our educational system was putatively designed to serve. These are the ranks from which future tech workers are supposed to be drawn. After the top schools and employers skim the highest performers for research and advanced product development, the biggest interest most employers have is what software students can use on day one. Most are less interested in what job applicants know about data structures than whether they've already had Microsoft or Oracle certification. You see the pattern. Employers think that college students aren't well prepared for the job force. College professors think that high school graduates aren't ready for college. High school teachers think that middle school teachers haven't prepared their students adequately. Middle school teachers want elementary school teachers to start keyboarding. Pretty soon we're going to have computers in the Montessori room. It seems that the answer to poor STEM is more STEM. That truth should make you angry. Most of my K-12 classroom experience is overseas, and the story is largely the same there, at least in the countries that I've taught. There are modest improvements that we can learn from each other, but I'm sorry to say that if you want to see a fundamental change, it's going to be up to you. Now, I've created an intentionally bleak picture to make a point. The reality, at least in terms of students' prospect of a rich and fulfilling life, isn't that stark. Most are resilient and creative. They'll achieve gainful employment, they'll have the opportunity to raise a family, and they'll become charitable citizens, regardless of whether they remember the half-angle formulas or where exactly a tree gets its mass from. That disclaimer aside, my point stands. We can do better. We can better achieve the stated goals of STEM programs than contemporary programs do, and maybe even for the top 10% of performers. How do we do that? We start by giving them the whole truth. The whole truth isn't more STEM. It isn't starting earlier and getting better outcomes on measures of mastery, in other words, teaching to the test. Neither should we ignore the advances STEM has made, retreating to some pre-modern technology as if the Enlightenment never happened. STEM fields are very well suited to the exploitation of the natural world. They build upon the fundamental nature of the world for a very narrow set of goals. My objection to the modern approach to STEM is not that its goals are too ambitious, but that they're too small-minded. That's not to imply that most researchers and engineers aren't genuinely interested in discovering for the good of humanity, only that the vision of what constitutes the good life, the purpose of education, human nature, wise government, and thriving communities, is treated like an abstract engineering problem. In September of 2006, Pope Benedict XVI spoke to scientists at the University of Regensburg about the inherent limitations of current science. He saw it as a twofold movement based on the fundamental rationality of creation. And I'm quoting him. On the one hand, it presupposes the mathematical structure of matter, its intrinsic rationality, which makes it possible to understand how matter works and use it efficiently. On the other, there is nature's capacity to be exploited for our purposes. And here, only the possibility of verification or falsification through experimentation can yield decisive certainty. If we accept the essential rationality of the created order, an enormous gift of the pre-moderns that was amplified and preserved by the church, then we're obligated to carry out the work of deciphering the natural world in a manner befitting good stewards. We have a moral duty to preserve both the roots and the good fruit cultivated by the giants who've gone before us, but also to remain firmly grounded in the humane and divine order that recognizes that the fullness of truth goes beyond experimental falsification. So what does a Catholic liberal approach to STEM look like? I don't believe that there's only one approach to this problem, and I don't think we have anywhere near enough experience with it to say what the best approach is going to be. But I think we can make some first attempts to describe a program that would be commensurate with the goal of broadly educating our students in humane mathematics and natural philosophy. I'm going to talk about 4 points that I think hold a lot of promise for us. The first is to take a narrative approach. The second is to tightly integrate STEM into the rest of the curriculum. Thirdly, emphasize principles over techniques. And finally, think very carefully about what kinds of technology you introduce to the classroom. Give me 1 second. As I mentioned earlier, our current approach to STEM is highly refined. What I mean by that is that we take basic facts and abstract them from their context, and we test them in isolation. And not surprisingly, we find that our students have a hard time solving word problems. Unfortunately, that's the only way that problems come to us in the real world. They're described to us. They don't come as pre-made formulas. Active learning, situated learning, and experiential learning are all techniques that are trying to solve this problem in various ways. They're trying to engage students in the physical and social context of doing science. However, all human knowledge develops already within a historical context. There's a narrative context already present, already at hand, if we choose to use it. Humans are generally very good at coordinating large amounts of information if it's done in narrative form. We prove this rule all the time with mnemonics, even as short as a single sentence, like King Philip came over from Great Spain, from memorizing the taxonomic hierarchy. You guys know this one? Right? If you think about that, right, it's for memorizing kingdom, phylum, class, order, family, genus, species. There is no economy of words in that mnemonic. You have one word in the mnemonic for each word that you're supposed to memorize. The only thing that makes it more useful than the taxonomic hierarchy is the narrative inherent in the sentence. It tells us a little story about King Philip coming over from Great Spain. You might be familiar with some experiments that they've done with nonsense syllable word lists, where they have students memorize 40 or 50 nonsense syllables, and then they give them some distractions, and then 10 minutes later, they have them try to recite the nonsense syllables that they memorized. The techniques where they teach students to put them into a story form, things that they call memory castles, are extremely effective, right? They work just like that mnemonic that we just looked at. And the reason that they work is that they create a narrative structure into which we can plug the information. Now, I'm going to maintain that those kind of memory castles are a very weak approach. And the reason that they're weak is that the narrative structure that we concoct to memorize that information has nothing to do with the information that we're memorizing. In fact, it's a tacit acknowledgement that the information that we're memorizing is nonsense syllables to these students, right? We want them to memorize the cranial nerves, so we give them a mnemonic to memorize the cranial nerves, because to most advanced bio students, the cranial nerves are just nonsense syllables. They just need to regurgitate it on a test. What could students learn if we presented this information in the full context of philosophy and mathematics? Let's take basic pre-algebra, introducing the concept of a variable. We usually tell students that we're going to use a letter like X, and that's going to represent some unknown number. And then we try to work out some progressively more complex equations. We'll start with something like x plus 1 equals 3. So like, what number plus 1 equals 3? And then we'll work up to things like 2x minus 1 equals 9. Entirely done in mathematical abstraction. The most significant work of algebra, at least for the way that algebra is done today, and the one that we owe the name algebra to, it was in the title of the work, was written in the 9th century by a Muslim mathematician, Al-Khwarizmi. Sorry, easy for me to say. He wrote the book as a guide for practical calculations in things like inheritance and trade. What if we started, instead of introducing X as an unknown, what if we started instead to think about, to ask students to think about how we might write complex expressions without the help of algebra? For example, can you think of a number to which you could add 4, then multiply that sum by 3, then subtract 7 from that product, and end up with 20? I'm just kidding. I'm not going to make you do that. So if you've had training in algebra, if you already know what to do, you're starting with this, okay, x plus 4, and then put parentheses around that, and then you'll multiply that by 3, right? You're going to go in that route. If you're a student who's never had algebra, most likely you're going to approach that problem in reverse. I need to end up with 20, and the step before 20 was subtracting 7. So the step before that, I need 27, right? And the step before that, I need to multiply by 3. So they're going to work their way backwards through that problem. But what they're doing when they work their way backwards through the problem is exactly what you do in algebra once you've got the equation, right? You start by adding 7 to both sides of the equation, and then you're going to divide both sides by 3. They're going to actually do that work in their head. Here's one that's actually in Al-Khwarizmi's book. Split 10 into 2 parts, such that the sum of each part times itself is 58. That's a little system of equations, right? X plus y equals 10, x squared plus y squared is 58. If you have students try that, it's just 10. They're just going to try, well, I'll try 1 and 9. No, that doesn't work. I'm going to try 2 and 8. No, that doesn't work. 3 and 7. Oh, there we go. We're just going to do it by hand, right? If you give them a bunch of those problems, you do 2 things. First of all, you teach them about word problems, right? That you can solve things without needing to put a number to them first. And the second thing is, they're going to develop for you algebra. Because if you give them enough of those problems, they're going to get tired of doing it in their head and working it out on pieces of paper, and they're going to start figuring out how to substitute what they don't know with some kind of placeholder, maybe it's a question mark, and then they're going to figure out how to write equations. In fact, the historical context for algebra is that there were all kinds of schools of thought on how you should write this stuff out. And there's notations going all the way back to Diophantus. Every discovery and every theorem has a story, a historical situation filled with characters and motivations. Even STEM purists have their heroes and villains. We see dramas like Galileo versus the Aristotelians, Oppenheimer and Truman's Oval Office. We've got explorers like Captain James Hook, Joseph Banks, and Charles Darwin. Innovators and inventors like Leonardo da Vinci, Thomas Edison, Antony van Leeuwenhoek. Scandals like the Alvarez hypothesis for the extinction of the dinosaurs. John Harrison's difficulty in getting paid for his maritime clock. And Boyle's and Hobbes' argument over what constitutes the value of laboratory evidence. And we have pioneering women like Ada Lovelace and Maria Curie. So we can at least tell an historical story and give some minimal motivation for students to get started. Something more than this will be on the test. But we can actually go much further. The second point that I made was to highly integrate the STEM sciences with the rest of the curriculum. As I've already mentioned, even in most classical or liberal arts programs, math and science stand apart. there's a general consensus that these subjects have their own internal logic. They're best learned in this rarefied form, and any other way of doing it is a muddle. It's hard to achieve, it's hard to assess, and in short, students really don't know enough to do anything meaningful. We don't feel that way about the rest of the humanities program. We feel like we're at liberty to swap in and out books that we think are important, to highlight different areas of historical context, to choose the art and architecture and music that we want to cover. We feel a lot of freedom with that, but we don't feel that same freedom with mathematics. It's got to be algebra, geometry, pre-calculus, calculus. It's got to be biology, chemistry, physics, then choose your advanced bio, advanced chemistry, or advanced physics. If you're in some of the more science-minded high schools, you may have access to things like environmental theory and so forth. But we've been approaching it that way for so long that we think that there's some kind of magic rule that it's got to be that way, right? We think that chemistry has got a pretty well-defined border, for example, what is and isn't chemistry. And what about biochemistry? What about ecosystems? What about physical chemistry? What about biomechanics? The boundaries that we set up are largely convention. Here's how I think about it. Mathematics is to natural philosophy as language is to literature. Mathematics is to natural philosophy as language is to literature. I don't always think in analogies, but this is one that I think is kind of helpful. Mathematics is the privileged language for describing the natural world. When we study mathematics by itself, it's very much like studying grammar and sentence structure. When we apply mathematics to the study of the natural world, to natural philosophy, it's like learning how to take what we know about language and compose poetry and prose. What if, instead of presenting mathematics purely within its own context, we always developed it as a means of describing the natural world? And what if, instead of every time we refine our natural observations or laboratory experiment, we develop the mathematics to better and better model it? Let's go back to my pre-algebra example. Where we left it in the historical context was essentially a solution to a social problem. How to communicate the solutions between people who might have different ways of approaching problem solving. But Al-Khwarizmi wrote his book to give everyone efficient ways to solve the problems of their daily lives. So those mathematics weren't just an abstraction for Al-Khwarizmi, they were actually a means to an end. Back in the pre-algebra world, if it takes 15 months, 517 days, to navigate from Lisbon around the Cape of Good Hope and back, a journey of 16,000 miles, what's the average daily speed of the vessel? Columbus expected Japan to lie about 3,000 miles west of Spain. If he expected to cover 150 miles a day, how long did he expect to be at sea? This isn't just using period content in the same mathematical expressions that we used before. This is an actual problem that a logistics officer would have to figure out when stocking those boats. If you're going to be at sea for 15 days, you need to stock a certain amount of fresh water and food. If you're going to be at sea for 30 days, you need twice that amount. It's an actual problem somebody had to solve. And then after we've done that a number of times, then we can ask students to themselves devise an equation that relates distance, rate, and time. The point isn't just to use the content of the area that you're studying. The point is to introduce the real-world context in which that mathematics makes sense, and then to make those problems progressively more challenging. Make the real-world problems more challenging, and develop the mathematics that solves those problems. So we move from the narrative form of mathematics to the integration of mathematics and natural philosophy within that same narrative, but we can go even further. In many cases, mathematics informed the arts and natural philosophy, and intractable problems in the real world occasioned the discovery of mathematics. In the former case, everything from music to architecture to poetry has both exemplified and paid homage to the mathematical relationships. So I want you to imagine a unit built around a single question. How do we know where we are? We can explore how cultures wrote about that, how they thought about it, how they depicted it, how they defined their place in the cosmic order, how their architecture reinforced that, how their art celebrated it, how organisms fit into their environment and find their way home, how species are able to migrate, how we use astronomy and magnetism, the difference between a map and the territory, how spherical geometry resulted in trigonometry and eventually global positioning. When the curriculum is fully integrated, the entire school is engaged in a common enterprise, and a more complete story unfolds. Many students will memorize and soon forget the difference between the North Pole, map north, magnetic north, and the pole star. But those who study that in the context of Columbus's first voyage, who see the math, read the logs, and understand the concerns of the crew, have a much better chance of keeping them straight. And I realized I should probably unpack that. As they moved across the Atlantic, many of the crew members noticed that the compass was not pointing to the North Star anymore, because they were, of course, the compass points to magnetic north. And there's some evidence that, that people knew about magnetic declination. As you move around the pole is pointing to the pole star, but your compass is pointing to magnetic north. But the crew didn't know that. And so they became very concerned, but they trusted Columbus's skill as an astronomer and believed him when he told them that it was pointing to a place on the Earth. So that's integrating it, a full unit that covers all aspects of the curriculum. And in a truly humane program, I think we need to go even one step further. None of the theories, method, or techniques that we have today were obviously true or right when they were first introduced, and none were immediately or universally accepted. Prior to Boyle and the rise of the Royal Society in Britain, experimental science and deductive reasoning had their respective advocates and detractors. Hobbes, for example, thought that anything that you did in a laboratory was a fabrication and didn't apply to the natural world because it was unnatural. In Galileo's day, astronomers were mathematicians who had no business making physical predictions. They were more commonly employed as astrologers. The degrees by which natural philosophy was reduced to empirical science and the consensus about which theoretical interpretations were to be given credence were and still are controversial. Engaging students in that dialogue gives them insight into the philosophical stance from which much modern science is done. As natural philosophers and mathematicians, we should be incorporating readings that expose pitfalls, and I'm just going to give you a few examples. Cognitive biases, like confirmation bias, Dunning-Kruger effect, and the base rate fallacy. These occur in science all the time. Confirmation bias is looking only at evidence that supports your theory, not looking at evidence which could contradict it. Dunning-Kruger effect is the tendency that amateurs have to think that they know more than they do, and experts to think that they know less than they do. And the base rate fallacy is looking at only the evidence in an immediate experiment or observation without considering the overall background rate of the occurrence of the thing that you're looking at. The thing about biases, cognitive biases, true cognitive biases, is that you don't get to correct them. They're subconscious. Your best hope is to learn about them and ask people to review your work, because they have a much better chance of identifying your biases than you do. On the other side, we have logical fallacies, fallacies of deduction, and these you can train yourself to avoid. Things that happen all the time in the natural sciences, post hoc ergo propter hoc, right? The fact that X happens after Y does not necessarily mean that Y causes X. The naturalistic fallacy, moving from statements about the natural world to moral statements about how the world ought to be. Cherry picking, selecting data which confirms your hypothesis. Misapplications of heuristics like the law of parsimony, which we know today probably as Occam's razor, right? And the typical reduction of that is all things being equal, the simpler explanation is the better one. And so we pare away additional hypotheses that we don't need to explain a phenomenon. The problem with that is that often the pared down theory does not actually account for all of the original observations. And so that first part, all things being equal, gets dropped, and what we wind up with is something that's not equal. Another one that gets misapplied all the time, you can pick which one of these you like, the Copernican principle or the anthropic principle or the cosmological principle. This is the idea that we don't work from any privileged place. The most likely aspect is that we are just one in the standard the largest group of probability. We don't have a privileged position. So we don't ascribe to the universe anthropic goals or anthropomorphic principles. If you pan back from the galaxy and into the overall cosmos far enough, it all looks homogeneous. We're all in a similar environment, right? That gets misapplied all the time in areas that don't warrant that, where we really do have a special or privileged point of view. And lastly, one that's very pernicious, underdetermination, which you may have heard of as the Duhem-Quine thesis, which talks about in science, if you're given a series of experimental observations and you create a theory to account for them, that theory is not the only one. There's at least one other theory that will account for all those facts. Right? If you stick a metal in a Bunsen burner and it turns the flame blue, you can make some theories about why the flame, well, actually it's already blue. If it turns the flame red, Bunsen burners, burning propane and all that. If it turns the flame red, you might account for some theory about what the metal was that you burned, but you can always come up with at least one other theory for why the flame turns red that doesn't rely on the chemical composition of the material that you put in the flame. That's underdetermination and was pretty strongly argued by Pierre Duhem. And then W.V.O. Quine took that and expanded it in the middle of the 20th century. So while you're working to build lessons like this across the curriculum, I would encourage you to drop these in, salt the work that you're doing with these kinds of points. I know that there's limited time already to cover all of the topics that you want to cover, and you're going to have to make choices. You're going to have to understand what I can drop and what I can't drop. And in the next section, I'm going to talk to you about that a little more significantly. But these kinds of points, the underlying philosophical stances from which we do science, those things are incredibly valuable later on. When your students graduate from high school and they go on to college, those of them that enter, say, cosmology, most likely the last time they will formally study biology in their life was the 9th grade. What is it that you want them to keep with them all through their lives? Was it really the entire citric acid cycle? How many molecules move from ADP to ATP? Or exactly what role the mitochondrion plays in cellular respiration? Or would it be a lot more valuable for that student to understand how energy moves from the sun, our primary source of energy, throughout an ecosystem? Right? Understanding those basic principles are going to be more valuable for that student later in life than all of the individual details and techniques that may not have any bearing on their future career. Excuse me. Okay. Focusing on principles over techniques. This is a hard rule to follow. Every textbook, every standardized test, it's all about getting through the material, right? We don't have any more time to spend on this. We've got to get through the material. And college-bound students are rightly concerned on these standardized tests. They focus heavily on identifying and applying definitions and algorithms. And many of these tests are filled with gotchas. They exploit common misunderstandings to separate those who generally understand the material from those who just memorize the formulas. It is a well-attested tenet of the test prep industry that the way to beat these exams is to learn the format, review the rules, and practice, practice, practice. In the end, we get what we test for, what Jacques Barzun called recognition knowledge. Later, when students go to college and are required to demonstrate constructive knowledge, they find themselves ill-prepared. This is what Jacques Barzun said about it. Multiple choice tests, whether of fact or skill, break up the unity of knowledge and isolate the pieces. Nothing follows on anything else, and a student's mind just must keep jumping. True testing elicits the pattern originally learned. An essay examination reinforces pattern making. Ability shows itself not in the number of accurate hits, but in the extent, coherence, and verbal accuracy of each whole answer. Science and math consist of similar clusters of thought, and in all subjects, to compose organized statements requires full-blown thinking. Objective tests ask only for sorting. So considering the kind of assessments that you're doing, they're based around full units, whole groups or modules of thinking, not disconnected facts. I do a lot of assistance for students in test prep, especially for SAT. I have three children who are in high school now, and it's an enormous source of stress. And part of what makes it stressful is the fact that they get these questions like a machine gun, right? You've got 30 seconds to a minute on each question. You got to move on. This one, this, and they mix them all up. So there's really no coherence to the way the test works. We train them so that they can kind of act like Vulcans, right? And I don't know if any of you watched the old Star Trek movies, but there's one scene in which Spock is being tested after he's been brought back to life. And he just has to answer all of these questions in a row that are all highly technical. That's the way that we want our students to be. Somehow we just want them to have complete and total mastery of these basics. What any of them means, the SAT doesn't really test. But the fact that you know the basics is what's important. The problem is that almost all the test prep guides have this advice that they ask students to do. This one's in the 2017 SAT test prep. One way to eliminate answers on the math test is by looking for ones that are the wrong size or that are not in the ballpark. The catch here is that general validity check assumes a thorough understanding of the material. Where would students have typically gotten that? The assumption is that they were getting it as either explicit supplementation by the teacher or they were abstracting it themselves from all of the variety of problems that they saw. So we as educators are already supposed to be providing the principles and then expanding those with techniques. At the high school level, students are still learning how to make those abstractions. They need help in taking good notes, for example. So it's up to us to help them discover those principles and apply them. And I use the word discover very deliberately. You're far more likely to understand and retain something that you figure out on your own than something that I tell you. And I want to illustrate this. I only have 3 slides today. So hopefully you can see this here. Have any of you ever heard of Manhattan distance? Manhattan distance is really the distance that it takes to get around a city that has blocks, right? You have to stay on the grid. So I'd like you to take a look at this fake map. It's not really Manhattan, but it's similar to it. And I'm going to challenge you that if you start at point A and you can only go north or east, so only up or to the right, what's the shortest path to B? Now, don't raise your hand or shout it out. Everyone have a chance. Think about it. What's the shortest path from A to B? All right, so hopefully you've counted out a few paths and you've got your favorite, right? Tell me something about all of the paths from A to B that only go north or east. They're all the same. If you have to stay on the grid, you can't cut through any blocks. All the paths from A to B are the same. Okay, so I want you to tell me something about the perimeter of these objects. Don't spend a whole lot of time counting them out. Just tell me something about the perimeter. Yeah, they're going to be all the same. These are kind of related, right? No matter what path I take up here, up and to the right, it's always the same length because I'm on the grid. The same thing's true over here. No matter how I deform that side in, I always have to cover the same distance to the right and the same distance up. Now, I could have given you a theorem about polygons that contain only right angles and the perimeter of a circumscribed rectangle, and that probably would have been useless. And I could have explained, without showing you this, that as long as you're always moving in the direction of your destination and you're on a grid, it doesn't matter which route you take, right? And that would have been somewhat better. But instead, I let you try to come to the conclusion yourself. And if we had been in a classroom, and we had been only about 25 or 30 of us, I would have let some of you talk it out at the board. Maybe some of you could have argued one way or another. Maybe there would have even been a debate. Maybe someone would have taken the opposite opinion, and we would have had to use some arguments to convince the people who didn't agree that that was the case. I'm going to give you one more. What about the cross and the square? Once you get the intuition for how these perimeter problems work and how the grid works, I hope you also start to get an urge to get off the grid and just go straight to the point. I just want to go from A to B. I don't want to follow the grid. And if you get to that point, then you're ready for Pythagoras and Euclidean distance. And we can start talking about right triangles. Right? So we're going to work it up from an actual problem. Now, I don't know how many of you have ever lived in a city that's built up of blocks, but I lived in Manhattan for 2 years. And there's a lot of times when you're walking along and you just take the light that's currently in your favor, right, when you get to an intersection. If I know I've got to get downtown 10 blocks and east 5 blocks, I'm just going to take whatever blocks I can, and I'm going to, because it doesn't make any difference until I get to Central Park, and then, you know. All right. I want to, and let me just get rid of this because I think it's just distracting to have these things up when I'm not using them. All right, the last point that I wanted to make is to think very carefully about which technology you introduce into the classroom. I work in technology. I want to hire college graduates who understand technology and use it well. So I'm certainly not against technology. But I want to point something out. If you take medication, you are not doing chemistry. If you read about chemistry, you're still not really doing chemistry, right? And that's really the fault of, or the weakness in our AP program, right? We ask students in AP Chem to read about a lot of chemistry, but unfortunately there's just no time to touch a Bunsen burner or a graduated cylinder, right? So if you're just consuming it or reading about it, you're not actually doing it. And so not every time that you use technology are you actually learning anything about technology. And every time that you read about technology, you're not actually doing anything with technology. If you want to include discrete mathematics, the theory of computation, applied logic, signal engineering, large-scale data analysis, graph theory, or modeling in your high school curriculum, by all means, do technology. In the past, high schools found it helpful to offer a semester-long typing course and an orientation to library research. And I think that a modern word processing course and internet research course is entirely applicable, and we should think very carefully about it, and we should design it, and we should actually do it. But teaching students how to use the internet is a far cry from handing them or requiring them to bring a device and saying, you can now use the internet. There are very specific ways that technology can assist in education, but those ways are often not at the basis of one-to-one programs or flipped lectures. We weren't really thinking about how we were going to use that technology in the classroom when we decided that all the teachers need to start incorporating that into their lessons. And we also probably don't do a very good job in most places of telling teachers or training teachers exactly on how to use it effectively in the classroom. And so it winds up being a distraction. It's very challenging if you're in a mathematics class and you're asked to use a piece of technology that has no bearing on mathematics. You've got to try to find some way to incorporate it. So what are some good uses? Administrative computing for communication with parents, with students, and assignments, submissions. Completely useful. Highly recommend you think about it. Assistive technology, screen readers, audiobooks for those who need accommodations. Absolutely amazing. Really giving students opportunities that they never had before. Projection of information-dense visuals. For example, if I had tried to describe to you the map that I used for Manhattan distance in words, it would have been very difficult to describe it. But if I have an information-dense topic that really benefits from projection can help a lot. It certainly will save handing out packets of printouts. Recording and playback of speaking and listening exercises for modern languages. Really, this is just taking the place of the language lab and the cassette recorder, and giving us potentially more access to samples. Appropriate equipment for lab or field work. In many cases today, this does include software that runs on a tablet or a laptop. But consider paper collection of field data before you run to the tablet. There are things that you learn about recording data in the field with a clipboard and pencil that you might miss with the tablet and the laptop. Think about manual equatorial mounts for your telescopes before you run to seek and find motor drives on the computer. Yes, you can go right to the Pleiades, but the whole goal of astronomy isn't just looking at the Pleiades. It's trying to find it through the finder scope and then getting a good look at it, right? That's all part of astronomy, is understanding how right ascension and declination works. You have to make these decisions on a case-by-case basis. A compass is technology. The compass in your smartphone is technology. Which one do you want to use? I'm not going to tell you which is the better to use. I am going to say that you should deliberately think about it before you decide what to use. And though there are competing views on this, I still recommend against the use of ebooks for the most part. I won't go into all the reasons. You can go Google my name and Humane Review. I have a fairly lengthy article on that surveys the current research on this and shows that unless you learn to read digitally, you're going to have a harder time understanding things that you read digitally than if you read them in paper. There's all kinds of other issues. Before video lectures became the popular flip format, we used to ask students to read the book and do worked problems first before coming to class. And flipped lecture format is really just doing that, except that we've said for a long time now that students don't read, and that's becoming a self-fulfilling prophecy. We don't give them anything to read in math and science. And if you look at the books aren't structured with nice explanatory text anymore. It's just brief sentences like, you used to do this, and then a formula. Now we're going to do this, and then another formula, and then a worked out problem with side notes and margin notes. They might have call-outs of famous mathematicians or scientists in the margins. They might have little interest stories about this is used in this industry. But again, it's telling them about it rather than using it. And I have a last thing to say about the internet. This past May, the New York Times ran an article by Natasha Singer, and it was entitled, How Google Took Over the Classroom. It's primarily about how Google has insinuated itself into the educational content. But in doing that, Google has taken a de facto stance on the philosophical question of what education is for. And Singer records this interaction she had with the Google Education Apps Group director, Jonathan Rochelle. He said, referring to his own children, I cannot answer for them what they're going to do with the quadratic equation. I don't know why they're learning it. And then he added, I don't know why they can't ask Google for the answer if the answer is right there. I would respond to Mr. Rochelle that the reason you can't just Google the answer is because the quadratic formula isn't just a disconnected fact that takes up otherwise valuable memory space. It is a concise, coded representation of a body of knowledge without which the formula is either nonsensical or misleading. In fact, the only person for whom the Google solution is useful is for someone who already understands that body of knowledge. The trouble in my mind is that Mr. Rochelle seems to think that those two people are the same. Is it relevant to the problem that you want to solve that there are no real roots? Is it possible to have only one real root? What about the boundary conditions of the problem? If it's, for example, a parabolic trajectory that I'm trying to calculate, I have an initial height and velocity. The root in negative time is meaningless. That's why Googling the answer is ridiculous. The formula doesn't tell me any of that stuff. I need to know that before I use it. The idea that all the answers are already out there is another kind of utopianism. I illustrate it this way. Suppose you have an anthropologist that spent his whole life studying some indigenous people. Let's say it's the Yanomami in Brazil. He's very prolific in his career, writes lots of articles and books, and at the end of his life, he writes a summa of everything that he's learned over 60 years of research, and it's 1,000 pages long. And another member of his field, who doesn't specialize in this, but is very appreciative of his work, writes a fairly lengthy review of the literature on the Yanomami, and he includes a lengthy discourse on this researcher's work, his life work, in particular this last book. And then some of his graduate students get together and they're like, this is very interesting, let's put this on the Wikipedia page, and they do. And at the top of the Wikipedia page, they sort of agonize over a really good summary. And that summary shows up in Google when you type the question, who are the Yanomami? And that answer becomes the reduction of this man's life's work. Right? It is this one paragraph. Now, there's an entirely good chance that you can read dozens of this man's articles online already, either through journals or through Google Books or just on the website of the anthropology department of his school. But you can't get all of that knowledge unless you read it. Just like you can't understand the beauty and depth and power of Anna Karenina unless you read Anna Karenina. The fact that the information is out on the internet is not an excuse for not reading it. I love the internet. Extremely useful, have all that information at my fingertips. But if I'm going to sit down and do research on the internet, I know I'm going to be reading for a long time because I'm not going to get the information into my head and understand it and digest it any faster because I could get to it right away. And that's what I mean by actually having a course to teach students how to use the internet properly. Because otherwise, it's going to be shortest way to get my homework done. Who are the Yanomami? Oh, there's a paragraph. In every instance where we try to take a shortcut to truth or are satisfied with only part of the truth, the part that enables us to manipulate and control or satisfy the question, we wind up not with freedom, but with slavery. Allowing just one part of a system to grow unchecked or in disregard to balance of the entire system can be just as bad as allowing a part of that system to atrophy or die. Education considered holistically is just such a system. If we permit STEM to stand apart, directing a study exclusively to global economic interests and artificially isolating its content to context-free facts, our students will become mere instruments of that economy. Restoring the narrative and reconnecting science with mathematics, natural philosophy, literature, art, music, and history is not only a technique to achieve better understanding, it is the most reliable road to freedom. Thank you.